Anyway, so factor each polynomial completely. So I'll do one where it's a little easy, and then one where it's not, as straightforward. But the idea is that you're looking for factors of C that add to B. All right. So we're looking for, we have our, oh yeah, sorry, it doesn't line up. For me, it's page 18, but it's either 17 or 19. I can never remember which way it goes. But it's always a page off. So x squared plus 27x plus 50. We're looking for the factors of 50. All right. Now, if you get to a point where you can just do that in your head, that's great. That's what we're working towards. But for now, you may want to make a list. All right. So we look at the factors of 50. So one. I mean, you could make a raw list if you want. Like sixth grade style. But you could also just do it in pairs, like 1 and 50, -1, -50, 2 and 25, -2, -25. And you don't have to make the whole list. I mean, you don't have to make the list at all. Once you get to the pair that you see adds to 27, then you stop. All right, so we already have that pair here. The winning combination is 2 and 25. All right, so if you want to keep continuing with or maybe you don't recognize it at first glance, or maybe you like to make the whole list first and then, all right, now I'm going to sit down and look at my list. That's fine too. 3 doesn't go into 25, 4 doesn't go into 25, I'm sorry, 50. 5 does, so 5 and 10, -5, -10. 6 doesn't, 7 doesn't, 8 doesn't, 9 doesn't, 10 does, but we already have the combination including 10 and 5. And so everything after that is going to be a repeat. Right. Oh, so it's page 19. Okay. So we're looking for the factors in binomial form. The first term in each factor has to multiply to the first term in the trinomial, or the first two terms in the factors. It's these two. A little off on my highlighting. These two have to multiply to this. All right. So the most likely possible pairing is x and x. All right. The factors of 50 that seem to make sense here would be 2 and 25. We verify by using the arc chart. No, that's not a good name. Arc diagram. Just to make sure that the 2 and the x, when multiplied and then added to the 25 multiplied by the x, will give you a 27x. And it does, once, or at least it'll be obvious when I clean this up. Oh, I lost a hat on my 5. Anyway, so those two entries do in fact add to the 27. So we have appropriate factors as long as these two numbers are positive. All right. So x plus 2, x plus 25. All right. So sometimes you have negatives. Sometimes you have cases where the factors aren't quite as obvious. There's a lot of different possibilities. Sometimes you have something like number 4 where there's a leading coefficient. All right. So if you look at number 4, you see that leading coefficient. You go back to what we were doing yesterday with that flow chart. The first thing you're looking for in any kind of factoring situation is a GCF. All right. So we don't try to do it using the most complicated technique that we've learned. We try to use the simplest technique. So I see that there is a common 3 here. So my GCF is equal to 3. All right, there isn't a common x across the board. All right, I have 3 numbers here, and I'm looking for a number, the largest number that divides evenly into each of these 3 numbers, the 33 and the 36. All right, the GCF can never be bigger than the smallest number that you have in your set. So I test to see if 3 divides evenly into each of those remaining values, and then it does, so we're good. Now, if you don't recognize that, or maybe the numbers aren't quite so simple, then you could go to Desmos or the TI calculator and use the GCD technique. So function, scroll down to GCD, take the 3 and the 3. That you probably shouldn't need a calculator to do. But then you get a result of 3, take that answer and compare it to the remaining value. All right? So you do the GCD again with this answer of 3. All right? That 3 goes in there, and then the 36. And you see that the GCD among the 3 values is equal to 3. All right? Same technique for the TI calculator, except it's math NUM option 9. All right? So it's in the math number menu. But you actually follow the same exact steps after that. So math, right arrow, go down to option 9, GCD, 3, 3, get that answer, do it again with the 36. And you see that the GCD is equal to 3. Right? Again, may not need to use the technology. If the numbers are simple enough, you shouldn't need to use the technology, but sometimes they're not simple enough. All right? So we divide each of these terms by 3. Hang on to the 3. We get x squared plus x minus 12. So now I'm looking at this trinomial as if it's its own problem. All right? So I'm going to look at factors of 12. So, just do that off on the side here. Well, in this case, negative 12. So negative 12, I'll start with 1. 1 and negative 12, negative 1, positive 12, 2 and negative 6, negative 2, positive 6, 3, negative 4. Oop, I don't need a comma there. Negative 3, positive 4. 5 doesn't work. 6, negative 2. Oh, wait, we already have the 6 and the 2s. So that's our exhaustive list. So out of the pairs of values here, I'm looking for the combination that will give us a sum of 1. Because, again, there's an assumed 1 in here. All right, the combination would be that negative 3, 4. All right, so we know it's going to be 2 binomials, x and x. Pop in my negative 3 and positive 4. Do my little rainbow diagram. No, that's not a good name. Negative 3x and 4x are the 2 products, which add to 1x. So we know we have our good factors, right? Because those 2 numbers add to the desired value of 1x. Just don't forget to bring that 3 along for the ride. That's part of the fun. And so this would be our final answer. All right, so it's got that extra step going on there. Right. So they can be a little funky. You see, down towards the bottom, you have a bunch of instances where you have that GCF concern, and then off on the next page, more GCF situations. So more complicated GCF situations, but definitely worth spending the time practicing. And I don't know why I did this, but there's a factoring by grouping problem in there for some reason. It's not a trinomial. There's 4 terms. It wasn't supposed to be a trick question. Oh, there's another one there too. These were only really supposed to be trinomials, so the binomials and the 4-termed expression shouldn't really be there. But it's good practice anyway, so why not? The activity tomorrow is going to have those kind of expressions in them. So, but the focus today is to get the practice on the trinomial stuff. So if you only focus on trinomials, that's fine, right? Or preferred anyway. How about number 8, and then we'll look at number 11 because it's right below it. All right. So factoring trinomials, if you remember, the result is going to be the product of two binomials. All right. So factor, factor. Now, the elements of these binomials are what make this whole thing challenging. All right. But we do know that if we have an m squared as our leading term, that the first two terms of the binomials, or the first term of each binomial, has to multiply to m squared. Right? So the most likely combination would be m and m. All right. But then we have to worry about whatever the c value is. In this case, a negative 24, and the corresponding factors. Those factors need to add to whatever the middle term is. All right, and that middle term has a coefficient of 2, so those factors themselves should add to 2, but one thing at a time, So we'll look at the factors of negative 24. So you start off with whatever comes to mind first, but I like to be procedural with it, so I start with the lowest possible value, which would be a 1 or a negative 1. So I'll say 1, negative 24, but then it could also be negative 1, positive 24. You could have a 2 and a 12, 2 and negative 12, negative 2, positive 12. Once you get to the winner, then you can stop, but until you get there, you just got to keep considering different possible factors. All right, so 3 goes into 24 evenly. So 3, negative 8, negative 3, positive 8. You could have 4 and negative 6, negative 4 and positive 6. 5 doesn't work. 6 I already have. 7 doesn't work. 8 doesn't. Well, 8 we already have. It does work, but we already have it. 9 doesn't work. 10 doesn't work. 11 doesn't work. 12 we already have. So we already have everything else. So I guess I could have tucked this in below. Maybe do a little shrinky dink here. There we are. So out of all of these possible combinations of values that are factors of negative 24, I'm looking for the pair of values that'll add to it too. All right, so just going through my list, I would add each possible pairing and say, well, will that give me a 2? Will that give me a 2? If you're careful enough, eventually get to the right possible combination. Unfortunately, in this case, it's the last one that we came up with, which means that if I followed this procedure, I would need to make the entire list in order to come up with the last value, which would be the correct one, but that happens sometimes. Okay, so negative 4, so minus 4, positive 6. Then I just do a quick verification. That verification is using the arc method. I still don't have a good name for it, I know that's not a good name, but the one where we draw the arcs. The arc of the covenant, the arc diagram, the Raiders of the Lost Ark. I don't know. So negative 4m, 6m. Those two values should add to give you the middle term. And that middle term was the positive 2m. All right. And negative 4m plus 6m is 2m. So we have our factors. All right. So that's one example. Another example is a case where you have a leading coefficient. Now, there's two types of cases where you have a leading coefficient. One is definitely more complicated than the other, but this is an instance where we have a GCF. So just going back to the flow chart from yesterday, first thing you want to look for when you're factoring is a GCF. All right, so I look at my three terms here and determine if there is a GCF that could be factored out. All right. If the answer is yes, we factor it out. If the answer is no, then we got to do the more challenging process, which we'll get more practice with as we go forward. Right. So I see a GCF here of 2, but maybe you don't. Hopefully you do. Bless you. We're looking for the largest number that divides evenly into the 3 coefficients. All right? The GCF can't be bigger than the smallest number in the set. So I have a 2, a 6, and a 108. It can't be bigger than the 2. All right? Well, if it's smaller than the 2, then it's just a 1, so that wouldn't be helpful at all. That's the trivial case. All right? So if 2 works, then that's your GCF. Since they're all even, 2 works. All right? But if you're not sure, you can always go to the calculator approach. If you're using Desmos, you use the GCD function under functions, well, obviously. Functions, GCD, type in the first 2 coefficients. You get a 2. Take that answer and put it in the GCD function along with the third value. Because it only works 2 at a time. Unless they change it, within the last 24 hours, but recently, that's how it's been working. All right, so 2, 108 gives you a 2. So that means the GCF is equal to 2. Same idea with the TI. It's just, as you know, you get there a different way. It's math, the math menu, right arrow over to NUM, and then you go on down to GCD. Then you type in your first 2 numbers, 2 and 6. Then do it again, math, NUM. Type in that answer along with the third number, 108. We only use the absolutes because the negative doesn't factor into the solution there. All right, so divide each term by the GCF. So n squared plus 3n minus 54. So now I have a trinomial. So I have to use my trinomial technique. All right. When we factor a trinomial, the result is 2 binomials, product of 2 binomials. I'm going to have that 2 out in front, so I hang on to that. But I have to be looking for factors of negative 54 now. So 1 and negative 54, negative 1, positive 54, 2 and negative 27, negative 2 and positive 27. It's like you get to 3. You're like, does 3 go into 54? So you check it, it's 18. So 3 and negative 18, negative 3 and positive 18. 4, does 4 go into 54? If you're not sure, you check it. It doesn't, but you can check it. 5, well, 5's the easy one, because if a number doesn't end in a 0 or a 5, then 5's not going to divide evenly into it. 6, all right, 9 times 6 is 54. 6 times 9 is 54. So 6 times negative 9, negative 6 times positive 9. 7 doesn't work. 8 doesn't work. 9 does work. We just did 9. So then everything else will be a repeat. So we get an exhaustive list of factors of negative 54. The thing is, you come across a situation like this and maybe you miss the obvious ones, or maybe none of them are obvious to you. I mean, the 1 and the number, that should be obvious. But maybe maybe it's just a number that doesn't resonate with you, like 51. I think I mentioned this before. 51, a lot of people don't know. You look at 51 and you think, oh, that's probably a prime number. Well, what goes into 51? 3 and 17 goes into 51. It's like, oh wow. I never thought of that. So sometimes you need the technology to kind of save you from yourself on that. All right. But anyway, we know we're looking for n and n. And the 2 factors, or the possible combination that gives you a sum of 3n, or sum of 3 in this case. So as it turns out, yet again, it's the last pairing, right, as I made my list. I didn't do that on purpose. It just worked out that way because I'm going in order. starting with 1, then 2, then 3, and just skipping anything that doesn't make sense along the way. Right? So eventually I get to -6, +9. I do my arc network. I don't know. So I get a -6n, a 9n. I'll reduce the size in a second, which will add together to give you a 3n. And so now you have your factors. All right, it takes a little doing. You know, it's not always going to be easy, right? But sometimes it will be easy. Thank you. All right. Now, what you're going to do for practice, you see there's a bunch of problems here, some of them more challenging than others. On this page, they're all trinomials. Honestly, on the next page, I kind of meant for it to all be trinomials too, but I put a mix of problems there. So, you know, you get some trinomials, some other than trinomials. You need practice with it all anyway, so it's fine. But what you're going to work on is, it says 18 on mine, but it's 19 and 20. So you can work together, work individually. But tomorrow we're going to do an activity. It's another one of those coloring activities. It's much shorter than the last one. It's only got 6 problems. So it's the one where you have the grid and you get the colored pencils and you draw it out. It makes an awesome picture, or at least in my opinion. All right. So yeah, it's only 6 problems. So it should only take you like 10 minutes. All right. But you could have as much time as you need. The remainder of the time in the class period tomorrow can be used for, you know, really any work that you owe me. If you're missing work, that would be the time to get it all taken care of. If you haven't had a chance to look at Schoology to see what you owe, you definitely want to make sure you do that. I know some people have reached out to me and we figured out any issues that might have been holding back people's grades, which is good. But if there's anything missing, it's going to show up on Schoology, so take a look, right? Because I have been getting emails where people are just shocked. They're like, I don't know why my grade is what it is. They're like, did you look at Schoology? And it's like, oh, okay, yeah. And it might be one of those zeros that's doing the trick there, you know. So, you know, just keep that in mind. For 10, we have k squared minus 13k plus 40. All right, this is page 19. So we have a trinomial here, and in the case of a trinomial, we want to look at the last term and use that to determine a list of potential factors. All right, well, definite factors, but potentially the correct ones that apply to the -13. So we need 2 numbers that are going to multiply to 40, but then also add to -13. All right, so when we look at the factors of 40, you know, take a systematic approach, unless the possible pairing jumps right into your mind, which can happen. You know, the more experience you get with this, the less work you have to do to get it right. But if you're thinking about a systematic approach, you start with the number 1 and think about, well, what would I have to multiply 1 by to get 40? That would be 40. But it could also be -1 and -40. All right, then increase from 1. Next up is a 2. 2 goes into 40 20 times. All right, but so does -2. -2 goes into 40 -20 times. 3 doesn't divide evenly into 40. 4 does. 4 and 10. -4, -10. 5 does. 5 times 8, -5, -8. And when you're constructing your list, you can stop when you get to the correct combination, but maybe you don't recognize it, so you keep going. So 6 doesn't work, 6 doesn't go evenly into 40, 7 doesn't, 8 does, but we already have 8 and 5. So everything else after that is going to be a repeat, all right? So what I'm looking for is the set of factors involving k and k, where the combination that we come up with has a sum of negative 13. So I'm going to go across the line here and say, all right, do these two add to negative 13? No. Do these two? No. These two? No. No, 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 no. Finally, the very last one is a yes. All right, negative 5 plus negative 8. All right. So that would be our two factors, or those would be the two terms. And we just do a quick check. All right. That check is really just a simple matter of verifying that the outer product and the inner product will add to give you the negative 13k. Right? So negative 5 times k is negative 5k. Negative 8 times k is negative 8k. Take the sum, negative 5k plus negative 8k gives you negative 13k. So these would be our two factors, k minus 5, k minus 8. All right, so that'd be it. All right, so that's a nice one. All right, but you still have to come up with the list, or you don't have to actually physically write the list, but you got to think about the possible pairings. So the question you're always asking yourself is, what are two numbers that multiply to the C value that also add to the B value? All right. So what, in this case, what are two numbers that multiply to 40 that also add to negative 13? Now, number 13, you see that you have a leading coefficient there. Anytime you have a leading coefficient, you want to be thinking GCF first. Actually, anytime you have a factoring problem, you want to think GCF first, all right, greatest common factor. It was irrelevant in number 10, but actually, honestly, looking back, I probably should have mentioned it because we should have checked to see if there was a GCF, all right? But I got a little lazy with that, slash, like sometimes when you have too much experience with something, you tend to lose sight of these things. And you'll get there. You'll get to a point where you don't even think GCF for certain problems because it's irrelevant. But for number 13, there is a GCF. There is a number that will divide evenly into the three coefficients that we see there. All right, and that number is 4. So our GCF is 4. My pen doesn't really want to work. There it is. All right, so we have three values here. The little strategy that I like to recommend is take the smallest number in the set of values that you have and see if that number will divide evenly into the other numbers. All right, doesn't always work, but when it does, it saves you some time. All right, so the smallest number that we have here is 4. Yeah, it happens twice, but it's still the smallest number. The smallest number is 4, and that will divide evenly into 4, 4, and negative 8. No, well, 4, 4, and 8. So I'm going to divide each term by 4. We hang on to the 4. All right, and that goes back to what I've been saying all along. If I said, give me two numbers that multiply to 15, and you're like, well, I know 5 is one of them. How do you figure out the other? You take the 15 and divide it by the 5. That gives you the 3, but you don't just throw away the 5. All right, you keep both factors. Here we have a number that divides evenly into our expression, and that's 4. We don't just throw the 4 away. We keep it. All right, so we're looking at v squared minus v minus 2. All right, so now we have a trinomial. So we go to our trinomial methods. All right, so we're going to look at this expression here, using the same strategy that I used for number 10. I'm going to highlight. Well, that negative v is really a negative 1v. So I'm looking for two numbers. Those numbers need to multiply to negative 2, but also add to a negative 1. All right, so if I'm looking off on the side here and saying, all right, negative 2, that's a nice number because, there's only so many factors. It could be 1 and negative 2, or it could be negative 1 and positive 2. All right, but there's no other possibility. All right, so you're looking at your two factors and saying, well, which pair, when added, would give me a result of negative 1? It would be the first pair. So my factors here Well, v and v is going to give you the v squared. So v and v are two factors, a positive 1 and a negative 2. Positive 1, negative 2. And that would be it. I was only going to do 2, but now I can't help but to look at number 16 and say, you know what, probably should do that one too. Because you got that power of 4 there. It's pretty scary looking. But remember, trinomial methods apply as long as the two powers, the two relevant powers anyway, are in a ratio of 2 to 1. All right, so if the second power is half the first power and there's 3 terms, then you're good. All right, we still look for a GCF. I don't see one. Each term contains either a variable or a number, but there's no instance in which you have a numerical GCF and also a variable GCF. So no GCF to worry about. So we take a look at that 36 and its factors. You know, you could get 1 times 36 or negative 1 times negative 36. 2 by 18, negative 2 by negative 18. 3 by 12, negative 3 by negative 12. You know, 36 is a fairly lengthy set of possible factors. All right, 4 by 9, negative 4 by negative 9. 5 doesn't work. 6 by 6, negative 6 by negative 6. 7 doesn't work. 8 doesn't work. 9 does work, but we already have the 9s and everything beyond that. All right, so I know I'm looking at 2 binomials. The first entry has to multiply to equal the first term, or the first entry of each binomial has to multiply to the first term of the trinomial. So then it's like, okay, well, what are our possibilities? It could be x to the 4th and 1, but that's not likely. Just like the other possibility or other problems, we would look at, for example, in this case, v to the second, that became v to the first, v to the first. This is really no different. We're just taking the exponent and dividing it by 2. All right, so this would be x squared, x squared. All right, so instead of x and x times x gives you x squared times x squared gives you x to the 4th. So now I'm looking for, out of my list, because we know they're all going to multiply to 36, we're looking for the pair that will add to negative 12. All right, so out of all of these possibilities, there's only one instance in which that happens. That would be minus 6. Minus 6, minus 6. Now, when you get to Algebra 2, you'll see that you could actually go further with this, but for now, that's as far as we can go. But you would look at each term and say, am I looking at a difference of perfect squares? Because anytime your factors aren't raised to just a power of 1, if they have power of 2, power of 3, power of 4, you got to be thinking that maybe you could factor it further, all right? And I don't say that lightly. You have to be thinking that. Like, you got to train yourself to think that way, all right? Power of 2. Oh, maybe I could factor it more. Power of 3, maybe I could factor it more. Power of 1, I can't factor that anymore. All right, but I see the x squared minus 6, and I see a difference. Remember, difference of 2 perfect squares is right in the title. Difference, minus sign, 2 things, each of which is a perfect square. Well, x squared is a perfect square, but the 6, that's not a perfect square. So we're that close, but not the case. All right, so what you're going to do with the remainder of class is just tackle a bunch of problems on pages 19 and 20. Right? There's a ton of them there. All the problems on page 19 are trinomials along the lines of what we've been doing in class today. All the problems, well, not all, but most of the problems on page 20 are a mixture of, pretty much everything, but they're primarily the difference of perfect squares, GCF, and the factoring by grouping. All right, so the priority should be to get the practice with the trinomials, but you should also try some of the mixed practice on the next page too. All right, so I'll freeze this up there so you can continue to dissect it all. But just like yesterday, I'm going to float around, help out, answer questions as needed.